Okay, thanks a lot. Thanks everyone for coming. It's a pleasure to be back and meeting everyone. Yeah, so if you think about learning in, if you think about learning in vision and NLP, we think about training models on broad, large, and diverse internet-scale data sets. But when we look at learning or policy learning in robotics, we are often looking at policies trained on a handful of objects in a handful of environments. And this is for good reason. Sparse reward reinforcement learning is challenging. So you need an expert to actually teleoperate and show how different tasks are done. But teleoperating robots is slow and difficult. And of course, there are practical considerations with taking physical hardware outside of lab settings to collect data. So the question that the field is actually facing right now is how can we scale up learning for robotics? And there are many answers to this question. People have looked at self-supervision, exciting work done here at CMU. You can, that takes the expert out of the picture. You can build arm farms, collect data in parallel. You can put robots in homes and collect diverse data that way. Or you can build capture setups which are flexible and can be taken outside the lab to, again, diversify data further. One could also do sim to real or train policies in simulation, get scale that way, and then transfer policies to the real world. The problem, I think all of these are going to be some parts of solutions, but they are not going to be the full solution, because even if you do sim to real for transfer, you first need to do real to sim in some ways to actually build a faithful simulation that you can train a model in. You can do the things on the top row, but they're still difficult to scale up because it's still data collection by people who are, you're taking robots outside is hard, right? What I'm going to talk about today is how can we scale up robot learning through observation of other agents solving tasks. Why might this be interesting? We do it as adults. And if you look at child development, it turns out this is a critical part of child development. Here is what Alison Gopnik says in one of her popular books. Nearly all animals, even slugs, can learn about the world through trial and error. Smart animals such as crows and primates can also learn by observing others. And human children take learning through observation and imitation to a whole new level. They use imitation pervasively to figure out how the world, other people, and their cultures work. So this is the backdrop with which I'm coming in. And I think my view is neither of these three by themselves will actually solve the problem, but all of them together puts us in a better footing. And in particular, I will focus on egocentric videos. These could be in the form of robots navigating around. So I could have a video of someone walking around and showing me how their house is, perhaps to sell it up or something. Or these could be videos which are capturing humans doing manipulation tasks in kitchens and so forth, right? So I'm going to work with these kind of, I'm going to look at these videos. Now, before I actually go into why, how we do it and so forth, it's useful to understand what does it have to offer beyond this vague motivation that maybe children and people do it, right? So why would such videos be useful for learning? And how can egocentric videos aid? It's much easier to collect videos, so we can get many more of them. There is larger diversity, might provide good generalization. If it so happens you find videos which are actually doing the task that you are interested in, demonstrations may directly show you how to solve the problem that you are interested in, right? So if you're in the business of opening locks, you can actually get videos of this form. You see, okay, there's a key that has to be inserted, then you rotate it, then then there is a handle that you somehow manipulate in order to open, and you're seeing lots and lots of these demonstrations, like different kinds of locking mechanisms work, right? So if this was a task you're interested in, you get rich observation data this way. But even if you don't have perfect alignment, even if you have videos only for tasks which are not exactly what you want to do but somewhat related, it still shows you what the world is like and how it works, right? So if you have a mundane video of this form, opening a cabinet, it tells you something about where do you interact with it, how do you interact with it, what happens when you do. Or this simple thing, this cable got stuck, this is not precisely the task you're interested in, but things can happen in the world, and you can build a catalog of how what all can happen. Now, so there is a promise over here. There is an aspect of scaling up that we can get if we can leverage these videos. The problem is it's not so easy. There is embodiment gap. what a robot can observe is different from what a human observes in terms of, let's say, right, what actions a robot can take, what embodiment a robot has, they may be different, right? I have a dexterous hand, a robot might not have a dexterous hand, might just have a parallel jaw gripper, and I would like to still work, still learn something for that. Videos don't come with motor labels, right? If you're thinking of behavior cloning policies, they need motor labels to train. Goals and intents are not known. Trajectories may be suboptimal, or they might be too clean, that you're only getting on-policy data. And if you're just learning on on-policy data, things don't quite work out, right? So there are many issues that one has to deal with. To circumvent these issues, what we have been trying to do is to learn at different levels of abstraction. I'm going to think about the control hierarchy. And yes, I'm interested in mapping muscle tension. I mean, at the very core, humans are operating with muscle tensions. And what I need to output is motor torques, right? But I can consider this hierarchy of representations that, it's muscle tensions, but maybe there was a macro action that I was trying to execute. Maybe there was some skill. There was some sub-goals. There is some goals in the world. And I can think of transferring at any of these intermediate levels of abstraction. And if you look at language, this is one way that people think about machine translation, that you're trying to translate from some source text to some target language. You can translate it word for word, or you can go up. You can understand the text, transfer in the more abstract space, and then render it back, right? So this is the picture I'm going to work with. And this somewhat addresses the limitations I had on the previous slide, which is that depending on the amount of gap that you have between goals, embodiments, and what we can actually observe in videos, we may benefit from different pathways, different level, transfer at different levels, right? So you might benefit from going up and then transferring and then rendering it back into the robot space. So there was a part 1 of this talk that I gave last year, and where I talked about how you can do this for navigation tasks. I'm not going to, how much I like all of those pieces of work. I'm not going to go into the details over there. I'm just going to give you a teaser of the kind of things we can do for navigation. And today, the focus I'll largely keep on how you can do manipulation for these tasks. How can you use this for manipulation tasks? So we have found benefits of applying this idea for navigation. What we have done is you can learn affordances, which is what can you do here, and subroutines, which is how. So let's say you have this kind of a video in a hotel room. You just walked out of it. Let's say you have this video. Once you have observed this video, you can go back in the first image, and you can essentially have that even though you're not observing the full environment, you have a pretty good prediction that in this environment, based on the perception that I have right now, I could go out and turn left, and that's a reasonable thing to do, right? So this is affordance. What can you do here? But also, you can actually separate out. You can get subroutines which can actually do this task, right? So this is some sort of an output. The affordance, you can actually learn from these videos, and you can actually predict. These are locations in the top row that you can actually turn left at. On the bottom, you're seeing some of these subroutines in action where you can initialize a robot at different places. It can actually execute this turn left motion reliably. And this was all learned from videos. We can actually also learn, and once you have these subroutines and affordances, you can start using them for lots of tasks, right? So you can just play these subroutines out in the world. You can get exploration for free. You can actually initialize a hierarchical RL policy, if you will, and you can get sample efficiency improvements and such. We have also extended this kind of a reasoning to reason about semantic layout, or what is where, right? A problem in navigation ends up being you're in a new environment, and you're trying to predict where is a likely object going to be without having seen this environment, right? And again, if you have a video of this form, you can actually start answering a question of the form, where is a couch likely to be, right? And you can use co-occurrence of objects and so forth to actually figure out answers to this and get supervision of this form just by watching how the world is laid out, right? So we did this. It you get good predictions for where can you expect an object and so forth, right? So and importantly, you can actually learn about where are objects even though you're not seeing them right now. So I'm looking for a bed. Based on this image, it can actually reason that okay, even though I'm not seeing one right now, it's being able to speculate going down this particular hallway that you're seeing might actually work out, and you'll find a bed, right? Yeah, so I think this is, we basically get like the semantic predictions. You can combine them with something that does navigation. So with some, you can use these semantic cues in a topological mapping framework. And what the kind of results you can get is you can actually learn effective exploration strategies. And these are actually much better than training with reinforcement learning in a simulation, or just doing imitation learning by throwing out the hierarchy, or doing RL plus IL. We can do better than those kind of things. Okay, so yeah, so I think that's kind of what we have talked about. And in this picture, what we did specifically for this work of finding objects in environments, we actually learned a value function which let us go up this hierarchy. And then we used something very specific to a robotics kind of a platform or a pipeline for navigation to render out, to extract behavior from it, right? So it's again this hybrid nature of things that you can do to get this to work, right? And we'll come back to this picture in other forms for manipulation. So yeah, as I said, today's focus is going to be manipulation. What I'll start out with is a project where I will sketch out at a very high level of how one can start thinking about manipulation or learning from manipulation from videos. So I'll start with that. And then I'll show what are some limitations of why it doesn't work or what else is missing and what we need to do. So I'll talk about, so I'll identify some shortcomings and I'll try to fix those shortcomings and so forth, right? So that's the rough plan for the rest of today. Okay, excellent. So I'm thinking about manipulation. I would like to have an understanding of objects in a way that, how can I interact with these objects, right? So think of this cupboard that you're seeing on the top right. To be able to manipulate and interact with objects, I would like to be able to understand what are possible sites that I can interact with this object. So like, cupboard handles are useful sites to interact at. How do I interact with those sites? Which is to say, I'm talking about human videos right now, so you would use like a adducted hand, thumb grasp kind of a grasp to interact with it. And then I also need to be able to understand what will be the effect of my interaction, right? What will happen if I were to successfully interact with it? Let's say I opened it, right? So a cupboard opens to reveal condiments inside. If you have some understanding of this form, so let's say I succeed in the training the models, kind of models I'm going to show you, and if you have a prediction of this form that at these locations, these are locations where you can interact at, and these are hand grasps that you can use to actually interact with it, you can now think about initializing a robot which can preferentially explore in these regions via some grasps or hand poses that are retargeted from the human human pose in some ways, right? So we could do that. That's not going to work out entirely, right? I mean, it will only be approximate, but it can guide your exploration, right? So that's what you get from A and B. If you can do C well, and you can actually distinguish what would happen after an interaction and before an interaction, you could in some ways train like a reward function or a dense reward function which can essentially say, okay, this is closed and this is open and there's a difference, and I can now try to incentivize the robot to get the state in situations where it has transitioned from closed to open, right? So these things can pop out. If I succeed at what I'm doing, it will be useful for manipulation in these kind of ways, right? Okay, so the question is, how can I extract this information from videos? And for this, that's kind of why I like videos for some of these things, is that you can hit the play button and you can get answers for lots of these questions, right? By observing what the hand is doing and how it is doing, it tells you about, it gives you answers to some of these questions, right? So this is, if you look at human hands in egocentric videos, they're informative. Attending to hand localizes and stabilizes active objects. That's useful. Hands show where all you can actually interact in the scene. And analyzing the hand, what pose it is exhibiting, and how it is changing around the object might reveal what state the object is in and how do you interact with them, right? So this seems like a strategy one can employ. So I'll give you, again, I think, so this is, so I'll give you some examples of how we have done this. So how can you predict affordances? What we did was something quite simple. You have models which can actually predict where hands are and what objects they're interacting with, right? So we have this kind of data. You can run these models. You can pre-process it in this way. You can actually label what grasp it is exhibiting. And now what you can do is you can mask out the hand. So I'll sample data around a hand. I'm going to mask it out because I want to predict where I can touch. If I already see it, I won't learn anything out of it. So I've masked out this region. So this is called, right? And now I can train a model to predict what I masked out, right? So in the masked region, is there a hand, and if so, where is it? You can think of this kind of a, you can set up this kind of a problem, and that will let you learn something, right? And we are predicting not just the location of hand, we are actually also predicting, in this case, what is the grasp being executed, and you can actually get supervision for both of these things. So it's some simple thing that one could do. If you do this, you can get results of this form. You can actually infer that here are sites for interaction. So you can pick up on small objects like doorknobs and so forth, that those are likely sites for interaction. You can actually infer that in this case you're seeing this plate. You can actually infer that you're more likely to interact with the edges of a plate rather than in the middle. You can get things like drawer handles, kettle handles, and so forth. We have some benchmark which we created for doing this kind of analysis. I won't go into the numbers, but it turns out you can actually combine it with object detectors. So object detectors are quite good. If you're trying to interact with a bottle, there is roughly no preference on where you're going to interact with it. So object detector is a good thing for objects like bottles and such. But when you get to concepts which are not very well represented in detection data sets, so this is an evaluation which is primarily focused on objects which are not represented in these things. Over there, you see a larger improvement in performance, right? So this is basically things like doorknobs and edges of plates and so forth, right? You can actually also run this kind of a model on, you can also get grasp labels, as I said, from this model. So you can reason that there's a precision disk kind of a grasp that you do with this tuna can sort of a thing, or like a parallel extension grasp that you can do on top of a box, right? Okay, so this is, indication of an answer, like a model that can actually do A and B in this particular slide. What happens when we do, what about the second question, right? So let me tell you about that. It turns out this question is a more nuanced question because the notion of what happens to an object, in some ways, what aspect you want to capture is very much dependent on the task you are interested in doing, right? And we wanted an approach which can actually work across tasks, and we do not want to subscribe that, okay, it's only going to be useful for these tasks. So the way we are thinking about this is to train a state-sensitive feature space, right? A feature space which is sensitive to the state that object is in, rather than the identity, which is what you get from training a model on large amounts of category-level data. And if you have a model which is sensitive to states that different objects are in, now you can actually extract task-specific knowledge from it by training a classifier which is sensitive to states that you actually care about when you're doing manipulation, right? And the recipe here is similar. We are going to look at videos of people interacting with objects. I'm going to now prepare data not across a single frame, but across a video, right? I'm going to, I have the object of interaction. I have the hand interaction track. I have whether this hand is in contact with this object or not. How is the hand moving around the object? I'm trying to capture all of these things. So this is the hand motion. What is the grasp label, right? So you can get tracks of this form. And now you can start doing some sort of self-supervised learning on top of these tracks. And we are adopting like feature learning method from that was popular then. I mean, we could replace it with something new right now. And this model is capturing essentially two aspects. One is I'm going to capture that objects are generally consistent in their state in time. But then when you transition once in a while, then you enter a different state, right? So I'm going to use temporal consistency in states to train this feature space. And this is what it looks like. You have an object track. Frames which are close by should have the same, should be similar in the feature space. And they should be far away from patches which are further down. And we'll use object hand consistency. So I'll also say that the features for this object should be similar to features for the hand as it is interacting with the object, and far away from hands which are not interacting with this object, is interacting with some other object. And the intuition over here is that even though the object identities are different, if the objects are in the same state, I'm likely to interact with them the same way with my hand, right? So there may not be commonality in the object track, in the appearance of the object, but there may be commonality in how am I using the hand around it. So this kind of a model lets you inject more supervision towards the state of the object. Right? Okay. So as I said, this feature is learned entirely without any task in notion. I mean, this is just a state-sensitive feature. But to test it, we have a small data set where we are distinguishing between states that objects occur in common kind of kitchen tasks. So we've annotated some images of this form. And now you can actually measure whether this state-sensitive feature vector is actually better at performance or not. right? And what we find is, yes, it does. I mean, you can look at in different settings whether you are training on all objects or you just have novel objects, and you see improvements in performance more so when you have novel objects at play. And you know, there's conventional wisdom. I mean, action classification is a typical thing people would do on videos. That does not lead to you focusing on object states because they're very coarse. You can train on specialized data sets on internet images which have object states, and those don't work very well either, right? Okay, so this was a sketch of what we had done, right? Now, any questions on this before I move on to what's wrong with this? Or maybe you can tell me what is wrong with this.
The C question, there are many actions that are possible for a single state, right? So you're just looking at some videos and that gives you just one possibility.
Yes.
How do you know all the possibilities?
Yeah, so I think that question was not very accurately framed. I think this is what we are doing. And then that's precisely the point I was trying to make, that the objects can, what matters for this object depends on the task I'm going to do. So I don't want to prescribe that, okay, for these tasks I want to learn a good feature space. I want to learn it across. If I have features which are sensitive to states, then I can, let's say I have some separate data for a specific task, what states I care about, and I can now train a linear classifier on that quite quickly. And that's the evaluation that we showed. It doesn't play into the notion that you only did one of the things you could have done, but others in other videos would have done other things with the same object, right? So you get data to contrast different things you can do with an object.
No somehow correspondence, right?
So we are not. Yeah, so I think the question that I have on this slide, I think I phrased it more inaccurately, right? So it's not a predictive model that, okay, that what is going to happen with this object. It's more like it's a feature space which is sensitive to transitions that this object can make. Yeah, so I should reword the question that I have on this slide. Okay, any other? All right. So now let me talk what is wrong with all of this, right? So what are the shortcomings that we are trying to fix? So hands were useful. They tell you where you can touch and so forth. They also let us learn state-sensitive features. But there is a problem that they are also a nuisance in the sense that to train this affordance model, there was a mismatch, right? I was masking it out, and then I was trying to make predictions of on pixels that I don't see, right? Which is a problem. I learned state-sensitive features, but if I just take these features and try to use run it on data from a robot, what you will see is this human-robot domain gap, right? Robot end effectors look different from human hands, right? So there is this domain gap that exists, right? So as is what we have trained, I think hands were useful, but they were also a nuisance. So we'll have to deal with this problem somehow. A second limitation you would have seen is that I'm only capturing 2D aspects of interaction, right? I'm looking at how the hand is moving in 2D and all of that, which seems quite unsatisfying, right? 2D hand motion around object is impoverished. I'm predicting grasp labels, but they're not really useful. A grasp label doesn't tell me how do I, this precision grasp is oriented how, right? So grasp label don't capture everything. How is the grasp oriented? Or they leave out non-prehensile manipulation kind of things, right? So this is a limitation as well. A third limitation, which is slightly disconnected, but I'll also talk about that, is that they only show on-policy data, right? The human goes to the bottle, just goes to the bottle, right? You don't get off-distribution samples, which are useful when you're actually executing a policy on a robot, right? So there's this well-known issue with behavior cloning kind of things that you only have supervision for what the human did, which is very good. Very often, if you are trying to behavior clone it or something, you will go off distribution, and now you don't know what to do, right? So there's this other issue, which is that we are only looking at on-policy data. So what I'm going to do next is try to tackle each of these problems and show you what we have done towards them. And hopefully, this advances our way of extracting things from manipulation from videos. OK, so I'll talk about first this notion of hands are useful, but also a nuisance. And what if I told you I can delete the hand and give you images which don't have hands, right? And that's kind of what we did in this work, where we are coming up with agent environment factored representations. So I have an image which has the agent and the environment both. I'm going to separate it out into an agent representation, which is essentially a segmentation of the agent, and an environment representation, which is the environment, what does it look like without the agent. So I'm going to I mean, if a few years ago, if diffusion models did not work so well, I would have thought about doing this factorization maybe in the feature space or something like that. But because these models do work quite well, you can actually do them in pixel space, and you can build representations on top, right? The way we do this is we have an agent segmentation model. It predicts segmentation masks for the agent. I mean, recognition like SAM kind of a model. And then we have an in-painting model, which is based on diffusion, which takes in masks and the actual video stream and produces images without the agent, right? So that's kind of what we are going to do, and this I'm calling the factored representation. This requires a model which can actually look behind hands, and to do that, you need understanding of strong priors on what do object appearances look like underneath, right, under occlusion. But you also might not be sufficient. So in this case, you have you don't predicting what is behind the hands over there. In this situation is not so easy because I mean, there could be bananas, there could be oranges, whatever, right? But because we have videos, you can actually look back in time, and you can see what object was underneath, and you can get supervision for it that way, right? So we need strong priors, which we are going to get from diffusion models trained on large-scale single-frame datasets, and we need visual history, which we are going to inject by letting this model attend to previous frames in the video sequence, right? So this is what this model looks like. It's a diffusion model denoising model, which this is a single image model that you download from the internet. And then what we are doing is we are expanding it to let it focus on previous frames, right? And the way we are injecting this previous frame information is by just modifying the attention layer, which lets us reuse all of the parameters almost, right? So cross attention to draw from previous frames lets us do this, right? So this actually works quite well. So you can actually, so here are some visualizations. So you get better performance on like metrics, but then you can actually recover strong priors, let you recover on the actual this thing, and then visual history lets you focus on what you would not have been able to predict purely based on priors, right? So this works quite well. So here are some visualizations. I was surprised how well this worked, and this is it's an easy problem in the sense diffusion models work quite well at in-painting. This is an easier in-painting problem because you can figure out where to steal from, right? That might be easier than just to synthesize all the content. So here are some images where we have painted out the hand, right, or the robot end effector, right? So here are some videos of things floating around in air, and the flickering you're seeing because of there's no temporal smoothing over here, and diffusion models like to recover the different modes, right? So here is another one. It's like drawers open automatically and cutlery floats around in the air, right? Yeah, so another example. As I said, you can do the same thing for a robot end effector, and I'll talk about what this green dot is in just a minute. Right? Okay, so this was the factored representation. How do I use this factored representation? What I showed you in the previous part of predicting affordances and subroutines, you can actually rewrite it in terms of this factored representation. I have the environment representation from which I'm going to try to predict the agent representation. And f is the function I'm trying to learn. G is the function which is deciding what aspects of the agent am I interested in predicting. Is it the location? Is it the 3D hand pose? Maybe it could be a retargeting of the hand to a robot end effector, something like that, right? So we can use this factored representation to do this task that I described to you before. You can actually also use this to learn or transfer reward functions from human data, right? You can learn reward functions entirely from human data, right? So we are going to do this. We are trying to learn this function f, and we are not going to run it on the agent image raw, but I'm going to pass it through a mapping function g, which I'll just talk about in just a second. And now you can actually use it to train a robot which has a different agent representation, but the same environment representation. And examples for G could be a simple example that we tried with was just the centroid of the mask, right? So roughly what matters is where is the hand in the image. So that's kind of what we tried with. You could imagine constructing a more complex function which retargets a human pose to a robot pose, and you can think of writing it in that way. That's another option. So what this lets you do is you can train a reward function entirely on videos from the internet, right? So this is actually videos from the Epic Kitchen, this open and close kind of a thing again. You can train this reward function, and now you can actually run this on a real platform in order to actually, in this case, open drawers, as we are seeing, right? And I want to draw your attention to the learning curves over here. So the reward function is transferred. Everything else is learned in the real world, right? So in the real world, it has to figure out, okay, how far I need to reach in order to pull it up and so forth. What you're seeing is on the x-axis is how many real-world samples you need for training, and how much on the y-axis is how much is the success rate that you get. And our method does better than, so this is using the factorization and everything. It does better than no in painting, which suffers from domain gap, but it retains the information that is useful for predicting rewards. And crucially, it actually also does better than in painting, but no factorization, right? So there's past work on this problem as well, which paints out the hand. I think we can paint out the hand much better because of these diffusion models. But also, if you need to keep track of the agent information, right? It is useful to know that I'm approaching the object. If you throw out that information, then you get a sparser reward. You only get a reward once you have actually moved the bottle. But by keeping track of aspects of the agent, which are in an agent-agnostic manner, you actually also get reward for approaching the bottle. And that's kind of why we are able to learn faster than like past methods, which only do the in painting but no factorization. Right? Yes?
Temporal factorization, is this what
So the factorization is just separating out the agent in the environment, right? And we are keeping track of, if you look at this particular picture, we are mapping this function g, which maps, so what passwork did was just not have a g, just have a f. But what this throws out is, okay, the hand was actually approaching the object, and you need to approach the object to be able to do this job, right? So keeping that around is helpful and useful. Yes?
I'm still trying to follow this setup. So here you have training sequences of someone with their hand opening the drawer. And so are there any demonstrations like on the robot platform?
There are no demonstrations on the robot. The robot is doing basically CEM. It's trying some things, seeing how much reward you got under the learned reward function, and then sampling more actions which will get you better reward. In this version, this is being trained on this particular drawer. The reward function is coming from internet data. The reward function is not coming from this situation, which is what some past works have done. The reward function is entirely coming from internet data. Now you can use that to optimize the policy, right? You can imagine I can do this many times over in the real world, and now I can get a policy for opening drawers and cupboards. I think this is not the most exciting application of this. This was just to show this difference between these different possibilities. I'll talk about opening drawers and cupboards in a later bit, but yeah.
Diffusion models are so great, why not just learn a diffusion model to predict how robot will look like in these scenarios? Because right now you're still missing the information of hand poses and stuff like that. Like those also give you information of how the robot
Yes. So I'm right now using the centroid of the mask. I could also retarget the hand and render the robot in over there. If you want to learn a diffusion model, you need the data to where the robot is actually interacting with the object. And that's not so easy to get, right? There are large-scale data sets, but yeah, so that would be a viable translation network, which maps would be a good thing to try. Yeah. You don't have paired data. I think that makes it slightly harder, but possibility.
How unpaired or paired is this video? It could be opening the top drawer versus the bottom drawer versus the middle drawer. Right?
Yeah. So
how does the robot know what to do?
Yeah. So this is coming from So it could be so if you look at any results of this form, which are saying, okay, with 4 CM iterations and with 20 samples per iteration, so in 80 samples you can learn something like this. The action space is constrained to make this happen. Otherwise, if you have a entirely free-form thing.
I'm thinking that it's very paired in some way. Appearance may not be.
Appearance is not paired.
The action is very paired.
The action is not. Like the human hand is not approaching it horizontally. It's might be approaching it in a different way. So it's not as paired as one would think. Yeah. The notion of which drawer, I think that is in this case constrained that, okay, it's the top drawer kind of a thing. Yeah. If you're interested in drawer opening and cupboard opening, I have better, more exciting things that I can share. Not from videos, but yeah.
At this time also, we're painting the robot hand to measure
Yes.
both
So we are in painting, and that also works quite well, right? So this is so this is a end effector. Just to collect data, that was easier to do it with this. But yeah, it does. You can actually paint it out. The robot hand is easier. It's a parallel jaw. Doesn't mess with the environment too much. Okay.
It looks like the diffusion model is not doing that well. The video looks like it's blurred, right? So somehow the robot still robot will never see a blurred version. Right?
Yeah, so you can pass it through. So some of the blurring comes from the vector quantization in the diffusion model. You can vector quantize the images at test time as well. So this is a thing that the student took care of. I didn't know what he did actually. I think there is blurring. I think some of it you can actually improve by making it temporally consistent.
If you need glasses, remove your glasses, you can operate better.
Yes. Yes, we have found. Yeah. So I think yeah, good analogy.
How would be the reward function just creating some change work in this example?
Create some change.
Yeah, because I mean now that you said that action space is limited, I am thinking action space is only possible one thing.
Yes. So I mean I think.
So like you keep doing things until something changes.
Yeah.
Opening the door.
So in this case, we were interested in this. What is the role of in-painting and factorization? That's why we set it up in this way. You're right. I mean, but if there could be more than one thing that you could do, then you'll have more trouble, right? Yeah.
Okay. So I should wait to see more results.
Not on this aspect, on other aspects. But so if you want to grill me on this, now is the time. But yeah, okay, can do it at dinner. Okay, so this was this first shortcoming. The other thing is we are only capturing 2D aspects of interaction, and the answer to this one would be to start doing some 3D pose estimation, and that's kind of why that's what we wanted to do. But 3D hand pose estimation in everyday egocentric images is actually quite challenging. So this is the output of the Frank mocap system, which people have used in the past. It does well to get the hand roughly in the same space, but it does not do very well in terms of predicting fine-grained aspects of how the hand is, right? So if you notice, the fingers are actually systematically less curled than they should be. And this was kind of the reason why we stuck with 2D reasoning, because 3D, in our view, did not work as well. So then we started working on improving 3D hand pose estimation in images. So I'll tell you a little bit about how we did that. So if you are working on hand pose estimation, you probably have seen Frank mocap. It's trained across lots of lab data sets. It does a few things which are quite good. It focuses on crops around hands to get a detailed view of the hand. And second, it's trained on multiple data sets, which lets it generalize well. Unfortunately, these are all lab data sets, because that's kind of where you can get 3D ground truth for hands. I'm going to talk about this ambiguity in 3D hand pose in crops. This is one thing that it doesn't handle, and I'm curious to see what you all think about this. And it actually does not generalize in the wild, because it has not been trained on in the wild data. So let me tell you about what is this ambiguity, right? So this is some in-progress work. So here's a case study. You have these parallelepipeds. So these are square front face, and the receding axis, the receding face could be actually oriented arbitrarily. On the very left, you're seeing a cube, right? It's placed right in front of you. And all these other ones are actually just placed, I mean, these are different parallelepipeds placed at the same location. Right? These are all different parallelepipeds. If you look at the relative 3D key point error or the absolute 3D key point error between these four to the leftmost image, there's difference, right? So the relative 3D key point is like 6 centimeters off and all of that, right? It won't be a surprise to you if I were to tell you that I can move these parallelepipeds, I can place them in the visual field such that the 2D appearance will be precisely matched up, right? You can actually do this by drawing the vanishing lines for this. These are all parallel lines. You can draw them and extend them, and you'll actually get them at this particular location, right? Now, when Frank mocap or any system for 3D perception takes a crop around the object and tries to predict either absolute 3D pose, absolute 3D shape, or root relative 3D shape, you have this problem that this neural network has the same input, but you're trying to predict different 3D output, right? And so if you just train it with the crop, it actually, on this toy problem, it actually does not train at all. You will get high residual error. But if you start taking the crop location as input as well, then you will not get this problem, and you will actually learn, right? We believe such an ambiguity might be happening in 3D pose estimation. So you can analyze hands in Arctic, and a hand could be in the top of the image. It's suffering a different foreshortening, but you can mimic the same foreshortening by being somewhere else in the visual field, but the hand is in a different pose. Now, there's enough ambiguity in single view 3D estimation anyways, but this adds some more ambiguity on top. And the empirical result we have is that by adding this crop location as input, consistently improves performance for hand pose estimation. And so that's something to keep in mind when trying to build such a model. And people have looked at this in the past, like the solution that we are adopting is something that exists in the literature or some minor modifications of that. So we are calling it intrinsic aware positional encoding, where we are encoding the direction of the ray at the different points in the bounding box that you're getting. And you can, so we are denoting the location of the ray rather than the 2D location in the image, because ray locations are more general representation. And you can compute it in a dense manner, or you can compute it in a sparse manner. And we have tried different variations of this in different experiments. So this tackles this ambiguity in 3D pose that exists in crops. It still doesn't generalize in the wild. And for that, we adopted this routine procedure that is there in the community, that we are going to use auxiliary supervision on in the wild data to improve generalization on in the wild data, right? So we have some hand masks on, masks on hands, so you can get those on in the wild data. You can't get full 3D supervision, but you can get hand masks that were readily available. You can actually also get some grasp labels. And now what you can do is you can say that my output should match in the wild data. I will differentially render my hand that I've predicted, and it should match the mask that I have, or the shape of the hand should be predictive of the grasp label. And you can train on this kind of auxiliary supervision in addition to the lab data sets. And now you get a model that actually does work much better on across metrics, right? So we actually have the best numbers on this Arctic 3D hand pose estimation benchmark, some convolutional models, some transformer models, wild hundreds are thing, and it actually improves both root relative shape prediction and where the hand is, both metrics. We have some control experiments where you can actually only ablate whether this position is important or this auxiliary supervision is important, and I guess this slide doesn't have it, but we have those kind of results as well. Yeah. So this is a comparison against Frank mocap. Frank mocap produces a flatter hand. With this, you can actually predict a better curled hand, which is good. It's not perfect, as you will notice. I think this hand still misses the fingertips that are over here, but it's getting better. Yeah, here's some other examples. You may be aware of this hammer model, which has been trained on a lot of data and so forth. It actually does not model this distortion properly. What it assumes is that the hand is in the center, and it puts a reprojection loss over there. But then if the hand is actually to the side of the image, and you take that prediction and put it on the side, it actually does not match up what the image is, right? So we believe we can actually add this trick to hammer, and it should improve performance. So we can basically train our model on just more data, and it should start improving. Yeah, so we are working on that, and we'll put out the model soon. All right. Any questions? So yeah, so this is our effort towards injecting better 3D information. You can think of repeating what we have done with 3D hand pose, with better 3D hand pose that we have, and that should help, right? Yeah, I'll talk about this compounding execution error. I'll admit this is slightly off from learning from videos, but this is going to be useful, and yeah, it's exciting. I'm quite excited about this, right? So again, I think the motivation is the same, that if I'm purely training on expert data, right, I have expert demonstrations that I'm training models on, the learner's trajectory might actually deviate from it, right? And now I'm in off distribution land, right? So this sample does not know what to do, because the expert only provided me actions at where the location, at where it was. And this is a compounding error problem. There's influential papers out of CMU multiple years ago. There's a strategy which is commonly adapted, which is dataset aggregation. You collect expert labels on the states that the learner is going to experience, label them, and then or get more data, and now you're in business, right? So this works. What we are going to do is we are going to use diffusion models to synthesize these out of distribution samples, right? Rather than having to collect it, we are going to synthesize them, and I'm going to come up with some sort of a labeling scheme that can actually come up with what is the action that I should take, right? And this was partly motivated by that the diffusion models that we worked in the previous thing worked so well, we thought this might be a good application, right? So yeah, by replacing data collection with data creation, we are going to improve sample efficiency of imitation learning. right? So this is, as I said, this is where the disconnect comes in. I'm going to show these experimental results with eye and hand cameras. These are not egocentric videos. These are egocentric in the, you can say, the pose of the in the robot hand frame. It's a camera mounted on the robot end effector, and now I'm trying to do different kind of manipulation tasks. There's also not human data, so there is a disconnect over there, but it's exciting, right? So I get these. I have this kind of a data, imitation learning with eye and hand cameras, and I'm, let's say, moving around objects. So I have data of this form. What I'm going to do is I'm going to generate an augmented data set, which is going to push the states out of distribution, get those images, get the corrective labels for them, so and then I'll go with it, right? How do we generate perturbed views? This is again a diffusion model which is trained on trajectory data. So I have an image, I have a relative transformation. Where do I want to go relative to this image? And I have what is the image going to be, right? So it's a diffusion model. We are adapting this specific one from ICCV last year. This is not our work, but we just took this. And it's basically doing this. So it takes in the image as input. This is the image that you're trying to denoise. This is the target. And you have the post conditioning again coming in as input via some cross attention kind of a mechanism. So that's how you can get the perturbed views, right? So that's image generation. You know the delta pose that you generated this image from. Now you need to generate the label. The way we get the label is you have IT tilde, which is the delta pose, and you have a subsequent image in your trajectory, in your expert data, right? And you know that you took action 80 to get to this next image. What we are going to do is our corrective action is actually going to be, you want to go from this delta p perturbed pose to the actual location that the agent went to, right? So this is what it looks like. So this is going to be move left, right? So the gripper moves left, the scene changes, right? Did something reasonable. This is move right, right? From the same image, you can actually move right. You're seeing this blurring, and if you notice this, this thing gets messed up between the original image and this one, and this is a vector quantization artifact. But yeah, that's what's happening. You can move forward, you can move backward, and so forth, right? There's an earlier idea which did this. You can actually think of doing this with nerves. The problem with doing this with nerves is that you can have nerves which work with deformable objects, but we were comparing against like a nerve which assumes a static world, and when you're actually manipulating an object, the world is not static, and so you can have different strategies. You mask it out, mask the object, don't mask the object, and all of that results in like a blurry kind of output, right? So whereas the diffusion model synthesized images look better. And you can actually, we tried this across 4 different tasks, and what we see is a consistent improvement over behavior cloning baseline, right? So the setup over here is you have this particular situation where you're trying to stack these cups on top of this box. You can train on some, and these are some holdout cups. So this is like a behavior cloning in the lab kind of a setting. And what you can see is you can improve upon behavior cloning by doing this kind of augmented sample synthesis, right? So I'll show you some videos. So this is pouring beans. This is the baseline, which does not succeed and creates a real mess to deal with. I guess I had, and whereas our method doesn't, and it's easier to clean up after that. But right, so you can do this kind of a pouring task. So this is not generalization. We trained the policy in the lab, and we're testing it in the lab, right? There's generalization in terms of like cup locations and lighting, but not drastic. It's not like I trained on my lab and you test it in your lab. I think we need many more demonstrations for that. Here's a shirt hanging task, which is you slide this shirt and then you pull it up, and right. So this is the baseline, and presumably our thing can do better. Right. Yeah.
Just to make sure I'm following. So the behavior cloning baseline here is just training on the demonstrations that all work.
Yeah.
And maybe there's a handful of them, like 50. And so you're generating more these fake demonstrations where it doesn't work.
So we are just going off distribution a little bit and giving it the correct label on that off distribution sample. What that lets you do is when you go off distribution, now you have a sense for what to do and how to come back to the distribution. In vanilla behavior cloning, if you go off distribution, then you don't know what to do, and now you could compound it over time. So by being slightly more robust to perturbations, you get this behavior, right? So Abhinav said it's robust.
The perturbation is small enough where you can just do some simple
Arithmetic, yeah, geometry to get the label. Yeah, it's a good question. How do you recover from more egregious errors? And that we don't. I mean, that will require more expert knowledge, right? If the bean spilled, now you need to figure out where to get a desk span from, and that is beyond what we can do. But presumably, we can succeed more often, or we can stay in the distribution more often. All right. So I basically showed you, how you can learn things at the low level. I gave some examples from what we had done in navigation. I showed you how you can learn common sense about objects and affordances and some kind of things for manipulation as well. I told you what was wrong about this, right? So, this notion of agent environment factorization, getting better 3D hand pose estimation, and dealing with this on distribution problem. I think in this picture, I think there is this dotted last line that one has to deal with as well. That you have learned something, but then you actually need to do something on the robot that might be specific to the embodiment of the robot and so forth. How do we deal with that? So in my lab, we also work on that. So I'm going to very quickly. So in terms of rendering behavior, we have done work on like whole body mobile manipulation. We have done work on like navigation in cluttered settings in agriculture. UAUC has lots of cornfields or soybean fields. And we've also done work on manipulation of formable objects, and which is all targeting this last mile or last centimeter kind of a problem that you know roughly what you want to do, but you actually, how do you do it, right? So I'll just tell you about this whole body manipulation piece, given I promised I'll talk about drawers and cupboards. So opening drawers and cupboards, yes, from videos we can actually infer, where should I interact with it and how should I actually interact to actually get the end effector trajectory. But now I also need a whole body motion plan that can actually accurately track the end effector trajectory, right? And the motion, and this is a well-studied problem. This is, you can use a motion planning approach. But the problem over here ends up being that because it's a constrained motion planning problem, states lie on low-dimensional manifolds that are difficult to sample from and so forth. So there's cost in terms of coming up with these plans. What we are doing here is we are going to take a machine learning approach. We are going to leverage past experience of solving similar problems. So we are not going to solve this on a single instance. We are going to solve it on a variety of instances. And I'm going to pay this cost at training time. But at test time, what I'm going to do is I'll take my end effector poses. I'll have a machine learning model which can directly predict the motion plan, right? And so this is this thing in action. So you can have a perception system which kind of detects these cupboards and drawers. It then goes to one of these locations that are promising for actually doing this kind of mobile manipulation. So it turns out that this location actually is it's a good one for opening a left, right hinged cabinet, let's say. And then you have some pre-grasp pose, some way of like grasping it. It's all coming from the mask RCNN that this is where the handle is. And then you now correct for the contact a little bit here and there. There's all some primitives at play. And then you actually run this whole body mobile manipulation plan, which can actually, I guess I wish it ran, huh? Yes, okay, it does run, right? So you can actually execute this. So it's like full like graceful motion. It actually conforms to the task constraint very well. And we did testing across UIUC on like there is so in this case we are training and we are testing on unseen drawers and cupboards. You take it to a new building. You put it in front of a cabinet. You say, okay, I want to open this cabinet, and you can do this. So we did some extensive testing across 13 buildings and so forth, and we got a 61% success rate. We've looked into what doesn't work. Perception doesn't work. The control was quite good. I think the perception was the missing piece. But anyway, I want to thank you all for your attention. These are some of the students who have done all of this work, and I'll leave some points up for discussion while I take more questions if there are any. Yeah, thank you.
Questions? So you have focused a lot on like these high-level stuff, and I think I was going to ask you about this whole can't play tennis thing. You almost like knew somebody who was going to ask it, so you said I will throw it into a discussion.
So I'm not going to argue that videos will take you all the way.
Yeah.
But I think they can let you do. They can focus you on the right, on things that, it can make it faster. But there is something to do with personal experience, and that you only get by.
So I mean, this is just an exploration, right? I mean, it's like a better prior for exploration. It's
You
not
can
really.
you can call it that. You can call it that, yeah. But you also get this thing that you're actually able to do it on data from all over the world, right? As opposed to if you're teleoperating a robot, you can actually only teleoperate it in a certain number of situations.
Also, I mean, have you looked into like more like
Dexterous hands.
dexterous hand manipulation? I think that would be where I think video is more, because most of these things
Good
are
point.
just like reaching and doing like a thing.
Yeah. So, good point. I think dexterous hands. I would actually, yeah. I mean, there's also a simulation pathway over there that has been quite impressive. I think what large data is helping us is generalization across situations, which can be used in conjunction with personal experience. So you can imagine I now need only a few behavior cloning demonstrations, and bulk of the learning got done on offline data. Yeah, but I'm not saying that, I'm not going to take a bet that I'll learn purely from videos and I'll show you robots. Yeah.
I would love to discuss more about your, first of all, great talk. I love seeing some of the work. I would love to discuss more about your point 4 here, because you're absolutely right. If we just kind of look at the agent, we only get a kinematic observation. But if we look at the environment, I think we can actually get a lot more. For example, if we see objects moving, we can reason that they could not have moved unless a force is applied to them. I think this is especially true for cooking, where you interact with a lot of deformable objects. And when interacting with deformable objects, it's even easier to perceive forces acting on them. Is this something that you've thought about? Is this something that you're interested in exploring, kind of moving towards object or environment-centric representations to infer things beyond kinematics?
So not in my own work. There's lots of work on tracking deformable objects through time. I think the kinematic part of it, I think there are models which can do, I mean, that doesn't work very well, but you can have point tracks which can actually do something reasonable. But that's again, like it's saying that, okay, this object moved in this particular way. Reasoning about what caused it to move is harder. I think we have done some work on that, but I think like reasoning about forces and so forth is not so easy. It's sort of ill-posed as well. Yeah, so I think that's a difficult, I don't have an answer. What I meant over here was, I can hammer something. I don't know whether how much force I applied. I could, hammer, but then precisely stop right against the thing, right? That does not, so I can't distinguish between them based on purely kinematic observations, or like kinematic observations from cameras which don't show too much deformation and such, right? So I think that's a problem which I don't know.
A very quick follow-up to that. To your first one, yeah, absolutely, we still need interactive learning. We can't, like, I don't think it's possible to kind of get exact forces from this. But I'm sure, like for example, in the hammering case, there's a wide range of forces that will get you to your goal eventually, that some just may take more strokes than others. And I personally believe it's probably reasonable to estimate, maybe it's not like exactly 20 newtons, but I know it is a light, medium, or hard force depending on how I see things move.
Yeah, so I'm not sure. I think maybe it doesn't break the object. How do you even observe? Yeah, it's not so easy. I think maybe there is something to do with, yeah, maybe you can notice the small deceleration that happens right before if I try to stop. But you need to be quite precise about it, perhaps. So I don't fully know whether that'll work out or not.
Okay, thank you
Yeah,
so much.
thanks. Yeah. Yes.
Okay. I'm a bit curious. How much of a limitation do you think it is that videos are just RGB, but robots are more than just a camera? Like
other kinds of other modalities as input, like haptic feedback or.
Other sensors you can get from behavior cloning or from doing sim to real.
Sim to real, yeah, fair enough. Yeah, so I think my view on that is that will basically come in point number 1, right? That when you do interactive learning, there you have all the simulation, all the sensors. What you can get from videos is more like generalization, that okay, this kind of thing worked on this situation, but it can also work on a lot of other situations that you have. And that'll be my response to it. Yeah, if it's other sensors which are more or less like geometry kind of things, maybe there is a bridge there because you can predict shape from images and such as well, and that works to some degree. But if you have other like haptic sensors, I think this is harder. Thanks a lot.